everyone, my name is Laura Doev. I'm a first-year PhD student here at the University of Cambridge, and I'm a member of the NIRCam side of the JADES collaboration. Today we're going to be talking about a very exciting result from the JADES collaboration and the James Webb Space Telescope, which is about the discovery and spectroscopic confirmation of 4 redshift greater than 10 galaxies. I'm going to be joined by Brant Robertson and Emma Curtis-Lake, which are 2 members of the JADES collaboration that had great impact in this work and were the lead authors in the papers describing and explaining these discoveries. Hi, Emma and Brant. So we're going to start, maybe if you can both introduce yourselves, where you're from, what you're mainly working on, and your role in the JADES collaboration. So maybe Brant, do you want to start us off?
Sure. Hi, my name is Brant Robertson. I'm a professor of astronomy and astrophysics here at the University of California, Santa Cruz. I'm affiliated with the NIRCam science team, and I serve on the JADES steering committee.
Thanks. Emma?
Hi, I'm Emma Curtis-Lake. I'm based in the UK. I'm at the University of Hertfordshire. I'm an STFC Web Fellow, which means that I get to do science with JWST and also have to take the public along for the ride in the UK. And I've been part of the NIRSpec team since 2016, and I'm most excited about looking at the build-up of elements over time with the incredible NIRSpec instrument.
Great, thank you. So the goal of this video is to talk about the 2 big papers that came out about the discovery and spectroscopic confirmation of 4 redshift greater than 10 galaxies. And so to start us off, maybe we can talk about the James Webb Space Telescope in general, and one of its main science goals being the search for these very distant and faint galaxies. So maybe, Brant, if you can start telling us a little bit about why this was such a big interest in the astronomical community, and what are the main questions that we're looking to answer with this telescope?
Yeah, absolutely. So we're really interested in finding the most distant galaxies in the universe. We know that galaxies like our own Milky Way must have started out somehow as little baby galaxies in the universe. And we want to try to find those kinds of galaxies and study their properties so we can understand both how they formed, but then also to get some picture of how they evolve into a galaxy like our own Milky Way. So the goal of this particular collaboration effort was to try to use the NIRCam images that we acquired with JWST, which are infrared images that can see very faint distant galaxies that are extremely red, to try to identify those galaxies, measure their properties, and then also to use NIRSpec, as Emma will tell you, to confirm their distances and to learn more about their detailed properties.
Right. Yeah, that sounds great. And Emma, do you want to add something maybe more on the spectroscopic side and how NIRSpec is really going to help in this effort for the fainter, higher redshift galaxies?
Yeah, so we've kind of been waiting decades to be able to follow up on a lot of the candidates in the early universe. We were able to find quite a lot of them with Hubble, and some of them we could confirm their distances, but it was incredibly hard. And now all of a sudden, thanks to NIRSpec, we can get hundreds of galaxy spectra at once. So we find all these galaxies with NIRCam, and then just with a single pointing, we can confirm them or not. And so this has already sort of helped with showing that one particular candidate at redshift 16 was actually at redshift 4.9. So we can see that it's very important for understanding the early universe to just make sure they are where we think they are.
Right. Yeah. And so bouncing off of that, I guess the reason we need these spectra is to measure the so-called redshift. So maybe can you give us some intuition on what we mean when we say a high redshift galaxy and why this is the quantity used to kind of age, in a way, these galaxies? Maybe, Emma, you can start us off.
Sure. So we use redshift interchangeably with kind of a distant measure, but actually it's a measure of speed, how quickly something's moving away from us. So as like an ambulance moves past us by the Doppler effect, we hear it going from a higher pitch to a lower pitch. And with light, what's happening is when something's moving away from you, it's shifted into the red. And if you can measure how much it's shifted, you can measure how fast it's moving away from you. And we know because the whole universe is expanding that the further away something is, the faster it's moving away from us. So if we can measure that speed that it's moving away, and then we have to use some sort of model of what we think the universe has done in the past, we get an estimate of its distance and how far away it is from us. And added to that, what's glorious about it is it's taken a really long time for these distant galaxies for the light to reach us. So we see them as they were billions of years ago.
Right. So it's not about seeing older galaxies, or rather galaxies in their older state, but we're actually seeing very young galaxies as they were right when they were first formed, which I guess is what's really exciting about this. Okay, so maybe we can jump into the 4 galaxies that were the object of these papers and this research. So maybe if you know off the top of your head what redshifts these were found at, and why this is kind of pushing where we previously could see with Hubble, for example. Brant?
The JADES collaboration has found 4 extremely distant galaxies. These are all galaxies that are beyond a redshift of what we call 10, redshift 10, which is really a milestone for extremely distant galaxies. Previously with Hubble in 2009 to about 2011, there were some candidate galaxies that were discovered in the Hubble Ultra Deep Field, which is the deepest area of the sky that Hubble observed in the infrared. And 2 galaxies in the Hubble Ultra Deep Field were thought to be above a redshift of 10. One of these galaxies, actually, Emma and I, when we were working in our collaboration, we've been collaborators for many years. In 2013, we co-authored a paper that said one of these galaxies would actually be at a redshift of 11.7, but honestly, we weren't 100% sure because Hubble just wasn't powerful enough to really pin down the locations of those galaxies. And then in the process of observing the Hubble Ultra Deep Field area and the area around it with JWST, we identified 2 other candidate galaxies that we thought were even more distant than that, above a redshift of 12. Actually, one as far as potentially above a redshift of 13. And so these galaxies, which we identified, the collaboration identified them in the NIRCam images based on their colors, looking for extraordinarily red objects that were not even present in the bluest images, but were identifiable in the red images. This is the kind of keystone observational technique for looking for extremely distant galaxies, very red galaxies that drop out in the blue filters. You don't see them at all in the blue color images that we take. We could then try to see whether or not those galaxies perhaps were actually as far away as we thought they might be just based on their colors. So then that's kind of where the transition to the NIRSpec team took over. So Emma, would you like to describe the rest of it?
Yeah, so after finding them with NIRCam, we had this very exciting moment where we realized we might actually be able to follow them up very quickly when we really didn't realize we'd have that opportunity, and we jumped on it because we were all together at a meeting in Arizona. And as you can tell, this is an international collaboration. Brant's across the pond in California. I'm over in the UK. So if we had not been all in the same place, I doubt this would have been able to happen. And when we got the spectra through, we could see this very distinct feature. And it's a feature which, in fact, is external to the galaxies. So in the early universe, there's tons of neutral hydrogen and helium that's left over from the Big Bang. And any light that is, we say, energetic enough to sort of ionize the hydrogen, which means to let it eject its one electron, then we don't see that light. That light is kind of used up by that hydrogen atom. So what you get is a distinctive feature where you have light and then it drops off. As Brant says, when you're searching for them, you have really red galaxies, and then in the bluer bands, you see nothing. And even if you were to look for hundreds and hundreds of hours, you'd see nothing. So we get these spectra through, and they have these beautiful sharp breaks in them, and we could pin them down. And the most exciting ones being those at 12.6, 13.2, that are actually further away than we could have found at all with Hubble. That's what's so special about these guys.
Right. Yeah, no, that's really interesting. So basically with JWST, we can see far enough into the spectrum that these breaks are becoming very clear, and we can very well measure these redshifts that perhaps before were more only constrained by photometry and not as well with the spectrum. That's really exciting. So I guess once you got all this data, you selected it with photometry, then followed it up with near spec and got these beautiful spectra. And then in your papers, there's a lot of work done in analyzing both of these data products. So can you tell us maybe about some of that analysis, starting with the photometry, and what maybe surprised you about these galaxies? What was something new that you saw that you didn't think or weren't sure you would find? So Brant, do you want to take us?
Sure, absolutely. So these very distant galaxies, we didn't know what their properties would be. These are the first ones this far away. So one really important thing that we need to do is to as you were saying, measure the properties, just learn something about what the characteristics of these distant galaxies might be. So one interesting thing is their colors. So the actual galaxy itself has stars that are forming. They have some stars in place already. And so this actually produces, as a function of color, different luminosities of light. And we can actually fit theoretical models to that information to learn something about the star formation rate or the stellar mass or other properties, the age of these galaxies. So that's one important thing that we did. And we found that they are forming stars at a rate that is comparable, a little bit less than the Milky Way is, but the stellar masses of those galaxies are like 100 times less massive than the Milky Way. So these are really vigorous star-forming galaxies for their mass. And then the other thing that the images give you is you can actually model the physical structure of those galaxies. You can look to see how big they are physically, how far across they are. And it turns out they're extremely small. Some of these galaxies are only a few hundred parsecs. That's an astronomer term for 3.26 light years. So only a few hundred light years across. And to give you some comparison, the Milky Way is like 100,000 light years across. So these are extremely compact galaxies that are forming stars at a rate for the mass, which is really phenomenal. So they're kind of interesting objects. We don't really have a full picture yet as to how they came to be quite like that. Our theories are still catching up with the observations, but they're a very exciting set of objects at the very distant parts of the universe that are accessible to us with JWST.
Wow, no, that's crazy. That's really interesting. Yeah. Emma, do you want to tell us a bit about something great that you saw that you weren't expecting in the spectra with these different emission lines?
Yeah, so I think when we first saw the spectra, we were almost disappointed, because one thing we'd love to see is fingerprints from different elements. So we might hope to see some spiky emission lines from hydrogen, oxygen, and they'll tell us how many heavy elements there are in the galaxies themselves. And they came through and they kind of look a bit featureless. And I think to begin with, we're somewhat disappointed. And then we started fitting to them, and we realized that this could actually indicate that it's really because heavy elements hadn't really built up a lot by this time, and that maybe it's not something that's unexpected at all. There's another scenario which it's not like it's super easy to pinpoint and say, okay, it's hardly got any elements. Another scenario is that maybe the birth clouds of stars, which is actually where those fingerprints come from. You have stars forming from clouds of gas and dust, and then the stars inside it are making that shine, and it's actually that will give you the fingerprints of different elements. It's also possible that maybe instead of the light being able to shine off that and bounce back to us, that actually it's getting through and escaping, and that would help us, because we know that over this time, the neutral hydrogen has to go in the interfeeding medium, has to go from neutral to ionized. So we can't quite pinpoint, whether it's lots of that escaping or whether it's really, really, really small amounts of elements, like 2% of what we have in the sun. But whatever we did, it was always less than 10% of what we had in the sun. So that's really, really... We say metal poor, and when we say metal poor as astronomers, it means any elements heavier than hydrogen and helium. So whatever we did with the analysis, it was all suggesting, that these are really early on, it's really pristine. There hasn't been tons of generations of stars pre-processing elements. However, we wouldn't say, and we wouldn't put a fingerprint on saying like these were the first generation of stars. Like you need quite a lot of evidence to say that. So, and there was nothing suggesting that they had no elements heavier than hydrogen and helium.
Yeah, that's very interesting. So I guess we're kind of forming this picture of these early type galaxies. They're very metal poor, very compact, but forming stars at a very high rate. And so do you think, what kind of image do you think this creates about how we view early galaxy formation, around what time this kind of all started, and whether even this small sample is maybe already giving us a clue about this, and or if maybe from other recent research, if you have, any idea of what kind of image this is creating for us, as far as we can tell with this data. Maybe Brant, you want to start?
Sure. The fact that these small galaxies in the early universe are forming stars quite vigorously, I really think it indicates that early star formation in galaxies has to be pretty efficient. They have to be able to basically form stars out of the gas and other the dust and gas in those galaxies very efficiently. It doesn't take very much effort for them to form stars, and there isn't a lot of resistance internal into the galaxy to forming stars. Another thing I think it indicates is that these galaxies, which are quite young, their stellar ages are not all that long. There could actually quite be very bursty star formation in the early universe. And these early galaxies are probably going through episodes where they form stars rapidly, and then maybe their star formation rates come down. And so we really need to understand better how these galaxies, first of all, form stars, but also how they're connected with the dark matter halos, the structure of the universe that's made out of dark matter that these galaxies start forming. And that's something we really don't understand well. And for us to really apply kind of the framework of theoretical models that have developed in astronomy over the last few decades to really understand how these galaxies form, we need to know that connection better than we do today. So that's really an exciting avenue of future research that I think we're all, really interested to participate in.
Mm-hmm. Yeah, no, that's definitely one of the big, because I guess, one of the other many reasons we want to study these high galaxies is because they have a big impact on the theory of how this all started and the underlying matter distribution and how this impacts how galaxies form and when. I don't know, actually, that was going to be a follow-up question. So if Emma, maybe you want to add on that as well, of what is something that you're really excited about to see in the following years of the James Webb, specifically within JADES, but just in general, what are we looking to do with this great telescope?
I think probably seeing the buildup of galaxies for the first time, because we can really see further back than what Hubble can see. So we can really characterize how it all kicked off and how it started. And it would be incredibly exciting if we did find evidence of those very first stars. So we'd just see the fingerprints of hydrogen and helium. That would make my day.
Yeah, definitely. That would be very exciting. Do you have any, Brant, any specific thing you're maybe looking more forward to? I know you kind of said more generally, but.
Well, I mean, I think the thing about being an astronomer, especially one in collaboration like this, is working with wonderful people and to have fun doing it. So, it's been a remarkable, just definitely a highlight of my career to work with wonderful people like the both of you, and to really kind of learn together. We're pushing back the knowledge of humanity. Like literally, we're really, pushing back into the early parts of the universe that we've never seen before. We're the first people that get to do that. So that's a real privilege. But also it can be challenging. And so having wonderful people that you work with that are a lot of fun to work with is really just a tremendous experience. So thank you both actually for your collaboration. Thank you.
Yeah, thank you. And thank you so much for coming here and for sharing a bit of your insight. And of course, for all the great work that you do. Everyone's really excited about this research. So yeah, thank you so much.
Thank you. Thank you, JADES.
Yeah, thank you, JADES. Great data.